We're tackling the problem maximal rectangle, and we're going to try and solve this with minimal complexities of OMN time and OMN space. In our problem statement, we're given a binary matrix of size rows times columns filled with zeros and ones. We need to find the largest rectangle that contains only ones within this and return its area. To give you a visual aid, here is the LeetCode example. Essentially, we'd be returning 6 here, because the largest area filled only with ones, our maximal rectangle, is that blue shaded area. So, you have 4 possible solutions here, 4 possible methods which will lead to a more optimal solution. They are A. DFS, B. Recursive approach, C. Prefix sum plus stacks, or D. Dynamic programming. I'm going to pause for a couple of seconds while you make your choice. Okay, so the answer here is C. Prefix sum plus stacks. And there is a caveat to this. We're using the monotonic stack algorithm, just as we've used with the largest rectangle in histogram problem, and as we'll use with a couple of others as well. The basis for this, I'd really recommend learning the daily temperatures problem and perhaps the next great element 2 problem as well. That'll help you prepare you for quite a lengthy solution here. Indeed, because of the length of the solution, I won't be going into any detail about a brute force approach here. I don't think it really helps us. What we'll be doing is looking at 5 different functions within our optimized solution. Some of them you may have seen before, however, if you've done some of the problems that I recommend. Now, to give a brief walkthrough of the optimized solution, I'm first going to expand this out, so just give me a second. So here we are, and that should be everything on screen. I've included a little text blurb here, which should be helpful, and essentially it's explaining what we're going to be doing. So if at any point you're struggling with the verbal explanation of the code, you can come back up and check this text and see if it makes sense for you. Of course, if nothing makes sense and all else fails, you can go to the Udemy course where Dr. Ibrahim explains this in much better detail than I can. Anyway, let's have a look at our functions here and see what I was talking about. I mentioned a prefix sum, and that's shown a little bit up above where we've got this example here. Essentially, we use the prefix sum to change the matrix we've been given into a histogram representation, just like in the problem, largest rectangle in histogram. And this is the prefix sum column variant, which we use upon the matrix we were given. However, we are given a character matrix. The zeros and ones are characters rather than integers. So we do a little conversion on the matrix before we enter it into the prefix sum function. Now, I'm going to explain more generally what our approach is. We're using this prefix sum method and a stack-based approach. The first thing we do is convert our binary matrix into an integer matrix by subtracting this 0 from each element in our matrix. We then apply the prefix sum column variant function to transform our integer matrix into a histogram. Each row in the resulting histogram matrix will represent the heights of the bars. Now, just give me a second while I find the largest rectangle in histogram picture to show you. So in this picture you can see a visual example of a histogram. And if we go back to the solution we're looking at, maximal rectangle, you can see that we're converting using the prefix sum column variant this over here, this matrix we were given, into a histogram representation. By the way, this is also the example matrix given in the example 1 by LeetCode. So we convert, and we've got our prefix sum column variant converting like so. So after we've done that, each row in the resulting histogram matrix will represent the heights of the bars as shown. We then use the stack-based algorithm, the monotonic stack, to find the next smaller element and the previous smaller element for each bar in the histogram. What we're actually doing there is we're finding the next smallest index and previous smaller index for each of these heights. So we've jumped into a different function here without me explaining it fully, but this function is very similar to the solution to largest rectangle in histogram, if not identical actually. We then calculate the maximum area of a rectangle by considering each row of the histogram as the base and applying this function to it. So after we've applied these calculations here, we should be returning the maximum area of all of the ones within our matrix, and it will obey the idea that we've got a rectangle involved. So all of the squares will contain a 1. So I noticed I was treading water a little with the explanation, so I'm going to jump into the line by line now to try and fully explain it. So first of all, this maximal rectangle takes in a vector of characters and it will solve our problem. We first check if the matrix is empty, returning 0 if it is, and happy days, that would make it a very easy problem. Otherwise, we'll initialize variables for the number of rows and columns in the matrix, create a duplicate matrix, here named matrix 2, which is the same size, and then convert the characters into integers by subtracting the 0 from each element. After we've completed the conversion into an integer matrix, we then apply this prefix sum column variant upon it. This converts it into a histogram. After that, we've got the max area initialized to 0, and then we iterate through each row in our histogram like so. For each row, we use the largest rectangle area function, or largest rectangle function, and we calculate the largest rectangle area comprised entirely of 1s, and we update the maximum area if necessary. After all that's done, we return max area. However, I haven't explained all of these functions. So, first of all, the prefix sum column variant. How exactly is that working? Well, it takes the matrix of integers and applies the prefix sum column variant technique to transform the matrix into the histogram. We iterate through each column of the matrix and update each element in the matrix by adding the product of two conditions, which is shown here. First of all, the element must be non-zero, and the corresponding element in the previous row is multiplied by it, which is here. This function has time complexity of OMN, by the way, which is where the complexity for our solution comes from. As well as that, we've got the largest rectangle function, which we jump into in line 104. So as you can see, we've got two arrays, next and previous. Now, these should be really the next smallest indices and previous smaller indices for each bar in our heights vector. We initialize a maximum area as 0 and then iterate through heights, which is our histogram representation. For each height, we get the left and right indices of the rectangle using those arrays, and then we calculate the area by multiplying the current height with the width, which is right minus left plus 1, updating the maximum area if necessary. Finally, we return that maximum area. Now, I'm going to go briefly into the next smaller index and previous smaller index functions, but I would recommend checking out the largest rectangle in histogram function, which goes into it in more detail. Essentially, next smaller index, or NSE, takes the vector of heights as the input, and we use the monotonic stack algorithm to find the indices of the next smaller index on the right side for each bar in our histogram. We initialize an empty stack and iterate through the heights, and for each height we compare the current height with the heights of elements on the top of the stack, as shown in that while loop in line 45. If the current height is smaller, we update the corresponding index in the result vector and pop elements from the stack until a greater height is encountered. If the while loop conditions are not satisfied, we'll just be pushing the index onto the stack. The previous smaller index function, PSE, is also taking heights as input, and after we create a copy of the heights array in res here, result, we reverse it and then use the next smaller element function upon it. Essentially, we get the indices for the next smaller element on the right side. We then reverse the result vector and adjust it using this for loop. And this will represent the previous smaller element on the left side by subtracting those indices from the size of our vector. Okay, so that's all of the functions explained, although I do think this is one of the most difficult problems in the course, and I would recommend checking out the Udemy course at all costs if you're really struggling to get this after 3 attempts. Anyway, I hope that I've helped point you in the right direction method-wise. So if you're asked about this, you should be able to explain that you can use a monotonic stack algorithm with prefix sum to help solve maximal rectangle. We've provided an explanation here, as well as some code in C++, Python, and Java as well. So, I hope that helps you, and thank you very much for watching. If you're following the learning mode of the Coding Card Sharp application, we'll be continuing with largest submatrix with rearrangements.